Good morning, student. I am very glad to inform you that today's video lecture is my 100th video lecture. I have no words to express my deep sense of gratitude to our Honorable Vice Chancellor, Professor Sachidanand Shukla, for inspiring us, for motivating us to prepare large number of video lectures related to our MSc and BSc integrated students. And I am very excited to inform you that so far the faculty members of our university, they have prepared more than 435 video lectures, and it will be useful not only for the students of our university teaching department, but also it will be useful for the students of the affiliated colleges. And I am really thankful to Professor Balwant Singh Thakur, who is the in charge of this lecture capturing facilities of Pandit Ravi Shankar Shukla University, for giving me this facilities to prepare the lecture. I am also thankful to the other faculty members of this department, Dr. Dipti Thakur, as well as Dr. Indra Kumar, and particularly today Dr. Rajiv Nayan, the research associate of our department chemistry. He is also here to assist me, and I am also thankful to Abhishek Katendra. Now today's lecture is very important because I must tell you that our Pandit Ravi Shankar Shukla University has been awarded by DST, that is called the DST Purse Grant, and the coordinator of that DST Purse Grant is Professor Manas Kanti Dev, and of course other coordinators are also there, Professor Shams Parvez, Professor Bisen. So we have purchased large number of state-of-art sophisticated equipments, and you are all aware of my first lecture. In fact, it is not lecture, it is lecture cum demonstration of the scanning electron microscope. So we are planning to prepare such type of hands-on experiment as well as the theoretical foundation of those instruments. So in that series, today I am thinking to discuss one of the most important concept of chemistry, as well as you can call it a material science, or even you all know about the MOF, metal organic framework. So that is the BET surface area analyzer and determination of BET adsorption isotherm, and of course we would like to determine not only the specific surface area of that material as well as the pore size distribution, etc. So I have divided this lecture into two parts. Why? Because you know that whenever we perform any experiment, it is necessary to understand the basic, I am not going to derive whole BET equation, but basic concept of this BET adsorption isotherm. So there are two parts. In one part, I will discuss the very briefly the fundamental concept of this BET equation, and secondly, in the second part, we will discuss the not only discuss, we will perform the experiment, that is, I have given the name, the hands-on demonstration of BET surface area analyzer, of course in our DST Purse laboratory, the advanced analytical laboratory situated in School of Studies in Chemistry, and particularly we will perform experiment today. And again, let me confess that I will use the instrument which we have purchased, that is Anton Par. The model is Autosor 6100. It is of course high vacuum piezosorption analyzer. So that is the introductory part. Now I am coming to the fundamental points. Now you know that in the part 1, what I am thinking, there are 3 parts. First is the understand the fundamental. That means you must know what is the genesis of that bit equation. Then something about the adsorption, although you are all studying adsorption from the BSc level. I will not discuss what is physical adsorption or chemical adsorption, but some elementary information about the adsorption isotherm, types of the adsorption isotherms, because these fundamentals form the foundation for understanding of that bit theory. So that is the first part. In second part, I will try to connect the theory with the physical meaning, because there are some mathematical derivations of the bit equation, but today I will not derive the bit equation, but I will give the bit equation final formula and the meaning of different terms, like what is P, what is P0, what is relative pressure, then what is the difference between the surface area and specific surface area. And third, the relate theory to experiment. That is very important. How, with this knowledge of this adsorption isotherm, how you can perform this experiment. That is very important, so that if you understand the theory, so you can confidently perform this experiment. Now, as you know that bit was developed by 3 great scientists, and it is a revolution in the surface chemistry, and they are from University of Washington, and of course he is Hungarian American scientist. His name is Stephen Brunner, and his assistant is Paul Amit, and third is another person, his name is Taylor. So Brunner means B, Amit E and T, and so they actually discovered, I mean they are working from 1930, but they first published this equation for the multi-layer adsorption in Journal of American Chemical Society in 1938. And there are large number of adsorption isotherms available in our, if you see the literature, there I think more than 10, but you know still that we are using, and most of the scientists who are working in the nanochemistry or material science, even pharmaceutical chemistry, they are using bit equation for surface area measurements and other things. And this is the historical paper of this bit equation, as I have already told you, Journal of American Chemical Society, adsorption of gases in multi-molecular layers. You see, this is the paper published by these 3 great scientists. And in addition to that, I am not, because my objective is to demonstrate the experiment, and very briefly I will discuss the theory and other things, but those who are interested to know more about the bit equation, their mathematical model, they can refer some very good books like Physical Chemistry Atkins or the Surface Chemistry McBain, and there are so many books. But I have seen one of the very simple paper related to the pioneers of the adsorption science, Stephen Brunner. They can also refer this research paper. Now I am coming to the subjects. Now the first question may arise that how do you define the adsorption isotherm? It is very simple. It is the extent of the adsorption of a gas on a solid surface at constant temperature with respect to pressure. That is called the adsorption isotherm. And naturally there are 2 parts. One is adsorbent and another is the adsorbate. In this particular experiment, our research student Dr. Rajiv Nayan, they have prepared some boron doped carbon materials, and you can use the silicon oxide also, or you can zeolite and other things as a surface. And particularly in that experiment we will use the nitrogen gas, which is very simple, easy to handle and other things. And you know that basically as I told you a few minutes ago, there are large number of adsorption isotherms are available in the literature, and there are some modification also. I will not go into details of these things, but since your BSc classes you are learning that French adsorption isotherm, that is the first adsorption isotherm, it is the empirical relationship, and in our MSc students they are performing the experiment using the activated charcoal and acetic acid or oxalic acid. So, it is a heterogeneous type of the system, and of course non-ideal and multi-layer adsorptions. But second, why Langmuir is important? Because you can call it that beat equation is an extension of the Langmuir adsorption isotherm. And Langmuir was awarded Nobel Prize, for the work of the surface chemistry. And the difference between the Langmuir and beat is in most of the cases Langmuir is the monolayer. But the area covered by that adsorb beat is also important. And we modified beat, they modified this equation, and that is called the beat equation, and it is a multi-layer adsorption. I will show you how we derive all these things. Now regarding some elementary features of that beat theory, because you know that there are some assumptions that there is no interaction between adsorbate to adsorbate. That is one thing. Second thing is that it is a monolayer, not monolayer, it is multi-layer, but we are considering the molecules on the surface. And a beat surface area analyzer is an instrument used to measure the surface area of a solid by adsorbing the nitrogen gas, of course at liquid nitrogen temperature. It condenses the nitrogen gas enough to allow the measurable adsorptions. And adsorption isotherm plots amount of gas adsorbs, usually in centimeter cube per gram STP, against the relative pressures. And then we can calculate various parameters, and thanks God now we are having a very good software. So, you need not to be worried about the cumbersome calculation of total surface area, specific surface area, volume occupied by the adsorbent. Nothing is required. Directly with the help of software we can calculate all these things. And these are very simple information about this French. I will not go into details because our objective is not to learn the French adsorption isotherm, but you can call it the extent of adsorption. That is, if you plot a graph between y-axis the extent of the adsorption with respect to concentration. If we are taking the acetic acid or activated charcoal, or if we take any gas. So, x by m Kp, actually it should be 1 power 1 to the n, and this 1 divided by n indicates the intensity of the adsorption, how favorable this adsorption. I have taken the photographs and the formula from the website. I have also given the name of the website, Wikipedia and other things. Now, why I am just concentrating on this Langmuir adsorption isotherm? Because this is the starting point for the beat equation. Although it was discovered in 1916 by this great scientist Langmuir, but you know that there is a very good correlation between this Langmuir and beat equation. If I just show you, if I take S is your surface and A is the adsorbate. So, it is a reversible process. So, I can write SA or AS, you can write like that. Then again this AS, another nitrogen gas is there. So, AAS I can write like that. Always that it is a physical adsorption, so it is a reversible, not irreversible. Then again I can write AAS plus again A. So, AAS. I am not going into details of all these things. So, I will show you some diagrams of other things. That theta is also important, the average fraction of the occupied site. And we consider that I am not also discussing the heat of adsorption. Definitely heat of adsorption is for physical adsorption is less, chemical adsorption is the irreversible process. Now you see that there are, because you are all MSc students and research scholars, you must know what is going on in the literature, and how already 100 years has gone. And because 2016 when Langmuir discovered these things, and today is 2025, so almost more than 100 years, 107 years. So large number of modifications, and there are large number of research papers on the 100th anniversary of the Langmuir theory. You see, there are beautiful papers in the American Chemical Society. I am not going into details of all these things. Those who are working on the nanomaterials or the material science or the MOF, they must refer all those research papers. Now I am coming to the main. Now as I am discussing, this is the schematic diagram of bit multilayer adsorption, and as you know that it is very similar to Langmuir adsorption isotherm, because generally in Langmuir there is only one layer is there, that is called the monolayer, and this is actually, I am just talking about the adsorbent, and it is just like a, here we are taking the boron doped carbon material and our gas is nitrogen. So you see that this first layer is that monolayer, and gradually as we increase the pressure, so you see these are the, and gradually the pore is filled up, and there are certain assumptions. One assumption is just like that, no adsorbate interaction. That means therefore we are taking the nitrogen. And second thing, that adsorption desorption equilibria is also exist, because when you plot a graph between relative pressure and the volume adsorbed, then of course you will see these things. So it is the adsorption desorption equilibria exist between the adjacent layer, and bear in mind that we are talking about the physical adsorption. So it is a reversible process. Another important point is that there are some unadsorbed gas molecules is also there. So it is a schematic diagram, and if you see different types of literature, you will get different types of very nice diagram of this bit gas adsorption on the solid surface. Now basically, as I told in my introductory part, that this surface area analyzer is very, very important in the area of material science. Must probably you are working on the nanomaterials, pharmaceuticals, environmental science, and it, of course, everything depends upon the types of your sample, and there are basically 3 types of things, and it classifies as per the pore size. As you know that if it is micropores, that means up to 2 nanometer. Most of the cases these are geolite, activated carbon, metal organic framework, like that. Then if it is in between 2 to 50, that is called the mesopores, where silica and activated carbons. And for macropores, others above the 50 nanometer up to 1 micrometer, 100 micrometer, 1000 micrometer, basically sintered metals and the ceramics. So as per their pore size, because in this experiment we are able to determine the pore volume is also important. Now you see that because we are using a very sophisticated Anton-Par bit surface area analyzer, so you need not to be worried about the calculation and other things. So automatically, with the help of KMO software, we can draw a plot, and you see that there are at least 5 or 6 types of adsorption isotherm. I am not discussing here the types of the adsorption. I am only concentrated on the bit adsorption isotherm, because the adsorption isotherm depends upon many things. For French adsorption isotherm, when there is a monolayer, the adsorption isotherm may be different. For Langmuir, the adsorption isotherm is, this is actually bit reason, you know, because when we plot, and this plot is not very good because I have taken from the instruction manual of this Anton-Par, it is actually relative pressure, and amount of gas adsorbed, you see this is a typical type of adsorption, and up to this it is actually monolayer part, and then there is a multilayer part, and this red color is showing the adsorption and this blue color is the desorption, and the actually bit region is this part is bit region. Now just for clarity, I am also redraw the curve. So here is relative pressure, you know, P by P0, and you know that one P0 is the saturated pressure and P is the equilibrium pressure, and here is the adsorbed volume, centimeter cube per gram in STP. So here is also same thing. One is red color is the desorption and A is the adsorption. As I told you that it is very simple type of the things. And but for the MSc students, sometimes we need to calculate these things. So it is a non-linear part. So for calculation of surface area, total surface area, and specific surface area, we have to calculate the Vm, then bit concentration and other things. So for that, I will not derive here the whole bit equation, because our objective is to demonstrate hands-on experiment on that bit surface area analyzer. So therefore, I am just giving only the final formula of the bit isotherm. But as we are having a very good software, so directly we can calculate everything. But for clarity and novelty, I am just giving this straight line graphs. Again, I am just giving here, you know that if I plot a graph between this, if it is y and this part is x, so this is the slope and this part is intercept. Now here for the student, I must say that this Vm is very important. In order to calculate the surface area and specific surface area, we have to calculate the Vm from slope and intercept. Now Vm is the volume of gas adsorbed at pressure P. And what about Vt? Or in some cases it is volume of gas adsorbed at pressure P and volume of gas forming on the monolayer. So this is very important part. And P is the, as I have already told, saturation vapor pressure of the gas. C is the bit constants related to the heat of adsorption, and you remember that it is a physical adsorption and extension of Langmuir theory. Works well for the physical adsorption, use determine the surface area of the materials. Now again for the student, MSc student, that you have to, yes. So it is a simple straight line curve, as I have already told you, is that when we plot a graph, it is a y-axis, because in order to get a linear plot, and this P by P0, automatically with the help of instrument we can calculate these things. So I have told you that this is the V mono, you can write mono layer, but it is Vm like that. I have written here V mono, so no problem. So it is a volume of gas required to form a complete monolayer on the sample. And after that, there is a equilibrium between the adsorption and the desorptions. So with that second part is the calculation of the Vm. So you can ask me, sir, why you are showing all these things, but if you have a modern bit instruments, so handle this automatically using the software. You have to do nothing. Just when we perform the experiment today, then you will see what is happening. But in most of the cases, that the relative pressure, which is very important, is maintained by the controlling how much nitrogen gas is introduced on the sample cell, because you just, it is a layer, surface layer, and that nitrogen gas is there, and you know that because we are using coolant liquid nitrogen and temperature is 77 Kelvin. So just our objective is to determine the specific surface area. So the student can also ask her why this is very essential, because it indicates how much surface area is available per unit mass, crucial for catalysis, adsorption and material characterization. So you see, simply it is slope and intercept. So Vm can be calculated 1 divided by m plus c. C can be calculated 1 plus m plus c. So the total area of all exposed surface of a material. So from slope and intercept, we can again and again, I am saying deliberately that when you are using the direct sophisticated instruments, you need not to be worried about all these calculations. But for examination purpose and for the student understanding, we must derive the bit equation, what is the definition of the surface area, what is the importance of the specific surface area, and ultimately with the help of simple calculation, total number of adsorbed molecules, we have to multiply with that Avogadro number, find the number of gas molecules in the monolayer. So these are all simple calculation, and because ultimate objective is that after the total surface area, we do calculate the specific surface area. That is the final equation, that is the specific surface area, you know. Specific surface area, and its units is meter square per gram, and if it is total surface area, so that is only meter square. And AM is the cross sectional area of the adsorbed molecule, weight of the adsorbent. And generally, when we will perform the experiment, you will see that we will take around 100 to 150 milligram of the substance, like boron doped carbon material. So this is the thing. So for student, I have taken one example from literature, that if our system is silicon oxide surface, so generally the surface area we have calculated 25.7 meters square per gram, pore size is 100 nanometers. I discussed with Dr. Rajiv Nayan. He told me that in his system the pore size is around 50 nanometers and surface area is 150 meters square per gram. So let me conclude that because our objective is to do experiment with that sophisticated equipment, but I think that before doing the experiment, student must know some of the fundamental aspects of the adsorption isotherm and especially beat adsorption isotherm. So in my second part, now after this fundamental information, now we will proceed for experiment. Again, now just some take-home message is that it is a homogeneous physical adsorption, very similar to the Langmuir adsorption isotherm, but here we are considering the multi-level adsorptions. Thank you very much.